Good morning, all. Today we are going to discuss bipolar junction transistor configurations, and also we discuss one of the configuration of bipolar junction transistor is common emitter configuration. Common emitter configuration, input and output characteristics, right? Okay, already we know that already we entered bipolar junction transistor. In last two classes we discussed BJT. Already we know this is the first figure. These three are the scientists' name who invented the bipolar junction transistor. And this is the first bipolar junction transistor, okay, in 1940s. And third figure is the what we see the transistor in nowadays, right? Okay, this is the third figure is the bipolar junction transistor what we are using laboratory. And here some information is given. The first bipolar transistor introduced by Bell Labs in 1948 was implemented in germanium rather than silicon material. Right? The first bipolar junction transistor uses the material germanium material, not a silicon material. And the thickness, base thickness about 30 micrometer, and provided a maximum operation frequency called some transit frequency of 10 megahertz only at that time. Now observe today's bipolar transistor realized in today's silicon integrated circuits. Okay, today we are using material is silicon material, silicon integrated circuits have a base thickness of less than 0.01 micrometer. Okay, the thickness is very small, 0.01. Now today, okay, at that time the book written that is the 0.01 micrometer. Now it will be again come down in terms of nanometer, right? Now the operating frequency increases to several hundred gigahertz. Okay, this is some information did you know, right? Now coming to the today BJT configuration. Already we know that BJT is a three-terminal device. One is the base, and second one is the collector, and third one is the emitter. BJT is a three-terminal device. Terminals are base, collector, and emitter. Right? What is meant by configuration? Configuration is an arrangement for making the transistor as two-port network. Okay, already we analyze in networks, right? Okay, what is meant by two-port? There is a one black box having some input side two connections, output side also two connections, and this is some current I1 current, and this one is the voltage V1 voltage I1 current. Similarly, right side V2 and I2. Okay, any network in this fashion. Okay, this can be analyzed using the two-port network parameters. Already we know two-port network parameters, Z parameters, Y parameters, ABCD parameters, H parameters. Like that we can easily analyze the circuit so that we can easily find the input impedance, output impedance, what is our admittance, input admittance, output admittance, voltage gain, current gain, like that, right? So configuration is an arrangement for making the transistor as two-port network. Okay. Here there are three terminals are there. To configure the transistor in different manner, that is one terminal is common for both input and output. Okay. Configure the transistor in different manners. One terminal is common for both input and output terminals. Okay, out of three, okay, out of the base, collector, and emitter, one terminal is common to both input and output, and remaining two terminals, one act as an input terminal and another act as an output terminal. Suppose consider here Suppose a emitter is common to both input and output. So emitter terminal is connected to ground. Now we can say that base is input. Base terminal is act as an input terminal and collector terminal act as a output terminal. So like that you can connect, you can configure the transistor, BJT transistor. Okay, using that concept there are three BJT configurations. One is common base. Okay, common base means base is grounded. Base terminal is grounded. Remaining collector and emitter terminals, one act as an input and another one act as a output. Next, common emitter configuration, CE. Okay, here first letter C indicates common and second letter indicates the terminal name, right? So common B indicates the base, common base are also called grounded base configuration. Okay, which terminal is grounded here? Base terminal is grounded, so that grounded base configuration. Next, common emitter configuration, CE, common emitter configuration or grounded emitter configuration. And last one is common collector configuration or grounded collector configuration. Okay, how we can configure the transistor? We can configure the transistor in three different ways, namely CB, CE, CC. That means out of three terminals, one terminal act as a reference point or common point between input and output. That is also called ground point, right? Remaining two terminals, one terminal act as a input terminal and another terminal act as a output terminal with respect to common point. Okay, input terminal with respect to common point, right? Output terminal with respect to common. Suppose input voltage with respect to common or ground terminal, output voltage with respect to ground terminal. Okay, these are the three important configurations of bipolar junction transistor. Okay, now we discuss one by one. The first one is common base configuration. Okay, here in common base configuration, okay, base is ground. Okay, observe here, these are all the terminal names. This is emitter terminal and this one is collector terminal and this one is base terminal. Okay, what type of transistor here? Whether it is a PNP transistor or NPN transistor. Okay, how to identify PNP or NPN? Observe the emitter terminal. In emitter terminal, the current direction is outward. In emitter terminal, current direction is outward. Now this is a NPN transistor. Okay, NPN transistor, right? Okay, here in when base is grounded, one terminal act as an input. Which terminal act as an input here? Emitter terminal act as an input terminal and collector terminal act as a output terminal. Right. Okay, these are all the current directions here. Okay, in a NPN transistor, always current flows from collector to emitter. This is conventional current. Conventional current, not electron direction is opposite. Electrons moving from emitter to collector and current is opposite direction, collector to emitter, and this is the whole current base. Okay, now already we know that in transistor what is the condition is emitter current is equal to base current plus, okay, apply KCL. Already we discussed this one. IE is equal to IB plus IC. Remember this one. Okay, anyhow, in common base configuration, emitter is the input, collector is the output. Okay. Now, in CB configuration, we have to find the current gain, DC current gain. What is current gain? Gain means output by input. Output by input. Okay, DC current gain is equal to output current by input current. Why? Because bipolar junction transistor act as a voltage controlled current device. Remember this one. So here mainly we concentrate on gain, current gain, not voltage gain here. current gain. Why? Because BJT property itself is voltage controlled current source. Okay. Now DC current gain is equal to output current by input current. What is output current? Collector current by input current, emitter current. Right? We know the transistor IA is equal to IC plus IB. If you neglect IB, IA approximately equal to IC. Now, if we consider this typical values here, suppose you can take an example. IA is equal to 200 milliamps. IB is equal to 2 milliamps. Why? Because base current is very, very small. Okay, maximum 5% only. Right. Now, alpha is equal to, this is alpha. In common base configuration, current gain is denoted as alpha. Alpha is equal to 98 milliamperes by 100 milliamperes, that is equal to 0.98. So now what is the range of alpha? Alpha range is equal to 0.95 to 0.98. Okay, in some problems, okay, a problem itself indicates that neglect base current. Neglect base current. When base current is neglected, IA is equal to IC, alpha is equal to 1. That means what it indicates, output by input is equal to 1. So gain is equal to 1. Here in this case, gain is equal to 1. Okay, maximum gain is equal to 1 if you neglect the base current, or otherwise, okay, less than 1. Gain less than 1, approximately 0.95 to 0.98. That is common base configuration. Next, coming to the common emitter configuration. Here in common emitter configuration, so that means emitter terminal is connected to ground. Remember this one. Common, here in previous, base terminal is connected to ground. Now here in this case, emitter terminal is connected to ground. Whenever emitter terminal is connected to ground, base act as a input and collector act as a output. So base terminal is input side and collector terminal is the output side. What is base current? Base current is IB, output current is IC. So in CE configuration, current gain is denoted as beta. So beta is equal to output current by input current. Beta is equal to output current by input current. What is output current here? Output current is IC, input current is IB. Okay, so beta is equal to IC by IB. Again consider the same typical values, previous typical values. IA is equal to 200 milliamperes, IB is equal to 2 milliamperes, IC is equal to 98. Why? Because IE is equal to IB plus IC. So 98 plus 2 is equal to 100. Right? Okay. IB plus IC is equal to IE. Now beta is equal to IC by IB. What is beta here? Now beta is equal to 49. Okay, 98 milliampere by 2 milliamperes, that is equal to 49. Okay, normally beta range from 50 to 500. Okay, nowadays it may be greater than 500 also. Okay, typical values 500 to 50 to 500. What is beta? Beta is the current gain. In CE configuration, current gain is up to maximum 500. Observe here, gain is very, very high, right? Whereas in CB configuration, gain is equal to maximum gain 1. Actually, in practically less than 1. For if you neglect IB, in CB configuration, current gain is equal to 1. But in CE configuration, what is current gain here? Current gain varies from 50 to 500. Okay. Now coming to the last configuration. What is last configuration? Common collector configuration. Okay, here in common collector, collector 1 is connected to ground. Okay, this is the collector terminal. Collector terminal is connected to ground. Right. Now observe here. Here it is a gamma. Current gain in CC configuration is gamma. Now here in this case, IB act as a input current, IE act as a output current. So gamma is equal to output by input, IE by IB. So same typical values consider here. For all these three configurations, we consider these are all some typical values or example values. IE 100 milliamperes, IB 2 milliamperes, IC 98 milliamperes. Now gamma is equal to, what is IE? IE is equal to 100 by IB is equal to 2, that is 50. What is the relation between gamma and beta? Here in previously beta value is equal to 49, because 98 by 2, that is equal to 49, that is beta. Now what is the relation here? Gamma is equal to beta plus 1. So in CC configuration, current gain is beta plus 1. Okay, these are the DC current gain comparison between CB, CE and CC. Okay, in CB configuration, the current gain is denoted as alpha. Alpha is equal to output current by input current. What is output current here? Output current IC by input current IE. So alpha approximately equal to 1. Similarly, in CE configuration, beta is equal to IC by IB. So beta range is equal to 50 to 500. Now in last CC configuration, gamma, current gain gamma is equal to IE by IB, that is equal to beta plus 1. Now compare here, out of these three configurations here, maximum current gain achieved in CC configuration, also CE configuration. Okay, here it one is CC, beta plus 1, CE is equal to beta, right? So that maximum current gain can be achieved using CE and CC configurations. Out of these three, CE configuration is most popular. Okay, later on we discuss why people prefer CE configuration while designing the amplifier circuits, right? Okay, here it one is the most popular configuration in BJT is CE configuration. CE configuration means emitter terminal is connected to ground, right? Now what is gain? Current gain is equal to IC by IB, that range is equal to 50 to 500. So gain is equal to, okay, it is nothing but amplification factor, that is equal to approximately, here we can take vary from 50 to 500. Okay. Okay, next one is now the relation between alpha, beta, and gamma, right? We have to convert or express one current gain in terms of remaining two current gains. What is alpha, beta, gamma? These three are the current gains in CB, CE, CC configuration. Now we have to express the one current gain in terms of another two current gains, right? Okay. Now here, first we express alpha in terms of beta and gamma. Okay. Alpha in terms of beta and gamma. Okay, first one is in terms of beta. Now what is alpha? Alpha is equal to IC by IE. CB configuration, alpha is equal to IC by IE. Similarly, beta means C configuration, IC by I. Observe these three expressions here, IC by IE, IC by IE. Now we have to modify the alpha in terms of beta. So we have to change this expression, okay, such a way that this expression, right? Okay. Now here which one is the common? IC is the common. So which one is the different? Here it is IE. So we have to modify the IE. What is the relation here? IE is equal to IB plus IC. That is the relation. So just replace IE with IC plus IB. Take common IC, IC common here. IC get cancelled. 1 plus IB by IC. What is IB by IC? IC by IB is equal to beta. So IB by IC is equal to 1 by beta. Then simplify this one. Beta plus 1 by beta. Then now alpha is equal to beta by 1 plus beta. Remember this one. So we know the current gain of beta. We can easily calculate current gain in CB also. Right? Okay, what is beta? Beta is equal to CE configuration current gain. We know the CE configuration current gain. We can easily calculate CB configuration current gain by using this expression. So alpha is equal to beta by beta plus 1. Okay, next alpha in terms of gamma. Alpha in terms of gamma. First of all, write down the alpha expression, then gamma expression. Observe in this two, in this two. Which one is the common? Here it is IE, here it is IE. So we have to modify the alpha expression. So we have to change IC or modify the IC. How to modify IC? By using this one. This is the standard relation between three currents. IA is equal to IC plus IB. From that IC is equal to IE minus IB. So IE here, IE common, only IC different. Change the IC. So modify IC in terms of IE and IB. So IE minus IB by IE. Take common IE get cancelled. 1 minus IB by IE. Now that is equal to 1 minus 1 by IB by IE. Here IE by IB 1 by gamma. So that is equal to alpha is equal to gamma minus 1 by gamma. So what is gamma? Gamma is the current gain in CC configuration. Alpha is the current gain in CB configuration. Once you know the CC current gain, we can easily calculate CB current gain. Okay, that is the first case over. What is first case? We are converting or expressing alpha in terms of beta and gamma. Next, another two. What is now beta? Beta in terms of alpha and gamma. Now, beta in terms of alpha and gamma. That means once you know the alpha value or gamma value, how to calculate the beta. Okay, first write down the beta expression. Beta is equal to IC by IB. Alpha is equal to IC by IB. Now, which one is common here? IC common here. We have to modify IB, right? Okay, why? Because there is no IB in alpha. Now, what is the relation? IB is equal to IE minus IC. So, IC by IE minus IC, IC get cancelled. Then IE by IC minus 1. That is equal to 1 by alpha minus 1. So, 1 minus alpha by that is equal to beta is equal to alpha by 1 minus alpha. So once you know the alpha, we can easily calculate beta. All these relationships are important. Relation between the alpha, beta and gamma. Express the one current gain in terms of another current gains. Right? Now second one is beta in terms of gamma. Okay. This is the beta expression. Beta is equal to IC by IB. Gamma expression IE by IB. So which one is common here? IB, here IB. So modify IC. So IC is equal to IE minus IB. So IE minus IB by IB. Take common here IB. Then again IE by IB minus 1. IE by IB is equal to gamma. Gamma minus 1. So beta is equal to gamma minus 1. Like that we can express one current gain in terms of remaining other two current gains. Okay, in third case, what is third case here? Gamma in terms of beta and alpha. Okay. Okay, third, what is gamma here? Gamma is related to the CC configuration. Beta is related to the CE configuration. Alpha is related to the CB configuration. Okay, now first one. Gamma in terms of beta. What is gamma? Gamma is equal to IE by IB. What is beta? IC by IB. So I have to modify the gamma expression. These two are common. Okay, we have to modify IE. What is IE? IE is equal to IC plus IB. IC plus IB by IB. Take common IB. IB get cancelled. IC by IB plus 1. IC by IB. That is equal to gamma. Gamma is equal to beta plus 1 by beta plus 1 or 1 plus beta. So gamma is equal to 1 plus beta. Okay. Next another one. Gamma in terms of, sorry, this is alpha. Gamma in terms of alpha. This one is alpha. Okay. Now gamma is equal to IE by IB. Alpha is equal to IC by IE. So here which one is common here? IE is the common. So here we have to modify IB. So what is the relation? IB is equal to IE minus IC. So IE by IE minus IC. So IE get cancelled. 1 minus IC by IE. So IC by IE is equal to alpha. So gamma is equal to 1 by 1 minus alpha. Right? Okay. Now this is the complete conversion between alpha, beta and gamma. A relationship between, sorry, relationship between alpha, beta and gamma. Right? Observe here, this is alpha, beta and gamma. Alpha, observe is the first row. Alpha in terms of beta is beta by 1 plus beta. Or alpha in terms of gamma is gamma minus 1 by gamma. The second row is beta. Beta in terms of alpha. Alpha by 1 minus alpha. Beta in terms of gamma means gamma minus 1. Next third one is gamma. Gamma in terms of alpha. That is equal to 1 by 1 minus alpha. Gamma in terms of beta, that is equal to 1 plus beta. Okay, this is the relation between three current gains, right, in three different configurations, right? Okay. Now we discussed one configuration characteristics, right? Okay. Already in previous class we derived this current expression, right? IC is equal to IC is equal to IS reverse saturation current into exponential VBE by VT. What is IB? IB is equal to, already you know the relation. What is the relation? IC is equal to beta times IB. IC is equal to beta times IB. Now what is IB? IB is equal to IC by beta. So this is IC by beta. So 1 by beta IS exponential VB by VT. Now here IE, what is IE? IE is equal to IC plus, third one, IE is equal to IC plus IB. And take common here, 1 plus 1 by beta, that is equal to beta plus 1 by beta IS exponential VBE by VT. Now observe in this expression here, collector expression mainly. Okay, this is the reverse saturation current is constant, right? This one is VT also constant, right? This VBE. If VBE is fixed or constant, IC also fixed. Remember this one. That means collector current mainly depends upon VBE. If base to emitter voltage is fixed, IC also fixed. Suppose here VBE is equal to 1 volt and corresponding collector current. If VBE is equal to 2 volts and corresponding collector current also fixed. Right? Remember this one. Okay. Now another one is bipolar transistor large signal model. Okay, already we discussed diode models, right? Okay, nearly we discussed there are 4 diode models. Ideal model, right? Consider the V gamma 1 model, consider the V gamma and RF 1 model, and consider the V gamma RF and RR 1 model. Okay, what is meant by model? Model is nothing but a we can replace when we calculate or analyze the circuit, we can replace diode or transistor with its equivalent voltage and current sources. Once we can convert the device in terms of voltage or current, we can easily analyze the circuits by using KVL and KCL, right? So that is a model helpful, right? Why people preferred modeling means once we modeling is nothing but a representation of device, either it is a diode or it is a transistor in terms of voltage sources or current sources or dependent voltage sources or dependent current sources. So now while analyzing the circuits, we can replace the diodes or transistor with equivalent models, right? Okay. Okay, observe here. This is the equivalent model, large signal equivalent model in CE configuration. Suppose if it is a emitter is grounded. Okay, for active mode, what is the condition here? For active mode, VBE base to emitter voltage is forward bias. Remember this one. For active mode configuration, base to emitter voltage is forward bias. Forward bias means here it is a junction diode, base to emitter junction diode. Here it is the plus and minus VBE, and polarity is such a way that this diode should be forward bias, right? Okay. Now what is current here? Resultant current here. Here the resultant current is IB current. What is IB current? IB is equal to IC by beta. So IB current, this is the IC current. So IC by beta. So IS by beta exponential VBE by beta. Okay, this is the IB current. So base current flows through the transistor in this fashion. Okay. Now when transistor is in active region, now there is a collector current flows here. This collector current, what is collector current expression here? This is the collector current expression. IC is equal to IS into e power VBE by VT. Okay, this current is replaced with a current source. Is replaced with current source. This is the current source. Like that is flows through the emitter. Okay. Always here current flows from collector to emitter in this configuration. Okay. A diode is placed between base and emitter, and a voltage controlled current source is placed between collector and emitter. Okay. Now here observe here. This is the current base current. This is base current IB. Such a way that base to emitter junction is forward bias. What is base current? IC by IB, IS by beta into e power VBE by VT. Now here it is a current source whose value depends upon VBE. Current source whose value depends upon VBE. VBE is the base to emitter voltage, input voltage. So current voltage controlled current source. Okay, what type of current source here? This is voltage controlled current source, VCCS. Voltage controlled current source. What is voltage control here? Input is the controlling. Input voltage is controlling. What is input voltage? VB, base to emitter voltage, is the input voltage. This voltage controls the current flowing through the collector to emitter. Remember. Okay. Now consider the characteristics of bipolar junction transistor here. Okay, which configuration here it is? Here the configuration is, observe here, this is the collector terminal, and this one is the base terminal, and this one is the emitter terminal. So emitter terminal is connected to ground. So this is the common emitter configuration. Okay, now we are in common emitter configuration. This is the simple black box here. Here emitter terminal is connected to ground here. At the output terminal is collector and input terminal is base. So what is input voltage here? Input voltage, this is common, right? What is input voltage? VBE is the input voltage, base to emitter voltage. VBE. We have to apply the bias voltage VCE. This is VCE. The configuration is CE configuration. Now we have to plot the input characteristics. What is meant by input characteristics? Observe here, output current versus VB. Okay, this is the one plot here. What is the output current here? Output current versus input voltage. Okay, now already we know the IC expression here. This is the IC expression. IC is equal to IS exponential VBE by VT, right? Okay, nothing but a diode. It is nothing but exponential is IC is equal to IS into VBE by VT. Okay, so this type of results a graph. Collector current, right? Now second one is. Now second one is, okay, here in this case VC is fixed. VC is fixed, right? Once again here, this is the graph here. VC is constant. Vary the VBE. Vary the VBE and plot the IC. Vary the VBE, input voltage, and plot the IC. Relation between VBE and IC is exponential relation. Exponential relation. Okay, like a diode. Diode VI characteristics. Okay. Next, coming to the output characteristics here. Here in this case, VB is fixed. Vary the VC. Vary the VC and plot the IC versus VC. What is expression here? IC is equal to IS into exponential VBE by VT. Okay, if VBE for different values, VBE1, okay, this is the collector current. So based on this expression, collector current is constant. Collector current is constant once we fix the VBE. Here VBE is equal to VBE1 is fixed. Collector current also fixed, right? Similarly, suppose VBE changes to VB2. VBE changes to VB2. IC also changes to IS into exponential VBE2 by VT. Remember this one, right? Okay. Okay. Here is the some simple problem here. What is the problem here? That means a given IS bipolar transistor, IS is equal to 5 into 10 power minus 17 amperes. Why? Because it is very, very small. Reverse saturation current 5 into 10 power minus 17 amperes. Beta is equal to 100. Calculate and construct the graphs. ICVBE, ICVCE, IBVBE, IBVC. Right. Observe here. First of all, calculate the graphs here. VBE1 is equal to, okay, where we, for graphs, we are taking some three VBE values, VBE1, VBE2 and VBE3. 700, 750, 800 millivolts. Okay, for all these three VBE values and resultant collector current IC1, IC2, IC3. Now we have to plot the graph, right? Now we have to plot the graph. What is the graph? First graph, IC versus VBE. What is the relation? Same as previous. IC is equal to IS into E power, what is here? E power VBE by VT. For VBE 700, what is this collector current? 24.6 microamperes. 750, 169 microamperes. 800, 1.153 milliamperes. Then VCE versus IC. Okay. Now for three values, okay, these are the IC values, these are the VBE values, this is a constant, right? It does not depends upon any other values. It does not depends upon the VCE. Whatever may be the VCE, collector current is constant. Only it depends upon VBE. Okay, for 700 VBE, this much of constant. 750, this much of constant. 800, this much of constant, right? Now coming to the another graph, IB versus VB. Okay, what is IB versus VB? What is base current is equal to? Base current is equal to IC by beta. Base current is equal to IC by beta. Okay, IC by beta. Already we have the IC values for different VBE. Then only divided by beta, IC by beta, 1.153 by beta, that will give us 11.5 microamperes. Then again 169 by beta. What is beta value here? 100. Given in the problem, beta is equal to 100. So like that, calculate the IB, right? Okay, then another one is IB base current versus VC. Okay, it does not depend upon VC value, whether it is a IC current or IB current, it does not depend on VC value. It depends on only VB. For different VB values, already we calculated IB, that is a constant, right? Like that, we have to solve the problems and also plot the graphs, right? Okay, this is about seed configuration characteristics. Okay, what type of configuration here? Common emitter configuration. Common emitter configuration. Okay, this is somewhat like a input characteristics. Okay, okay, this is output characteristics. Okay, okay, sometimes we may plot input characteristics. We may plot also IB also. IB input current by input voltage, output current by output voltage, or otherwise output current by input voltage, output current by output voltage. At the time remaining one is constant. So finally there are four graphs. What are the different graphs here? ICVBE, ICVCE, IB, VBE, IB, VC. In next class, we discuss another configuration characteristics, right? Okay, this is about CE transistor configuration.